Alrighty, so our next topic in probability is something we call theoretical probability. And so as compared to empirical probability, which was based on an actual experiment and actual data, theoretical is going to be totally based on theory or what could happen just based on the way an experiment is set up. Now, in this entire chapter, probability refers to theoretical probability unless stated otherwise. So when you just say probability, just assume it means theoretical probability. Another term we're going to need is something called equally likely outcomes. And these are outcomes that have the same chance of occurring. Now, the theoretical probability formula is basically the same as empirical with a little bit of a change. So P still means probability, E still means event, and so the probability of an event occurring now is the number of outcomes favorable to E divided by the number of possible outcomes. Okay, so now all we have to do is look at the experiment and say, well, how many times could E happen, or how many outcomes in that experiment would give you the event, divided by how many outcomes are there in that experiment that are possible. So we don't actually run the experiment, we just look at it. Now, the probability will still be somewhere between 0 and 1 inclusive. A probability of 0 means something slightly different now. This means that the event can't occur. And if we look at our formula, the number of outcomes favorable to E would be 0. Okay, so 0 divided by anything would be 0. And it means that the event can't occur. It's impossible. A probability of 1 means the event must occur, or it has to occur. And so what happens there is the number of outcomes favorable to E equals the total number of possible outcomes. So every outcome will satisfy the event. Okay, just a review of this formula didn't change. The probability of not an event is still 1 minus the probability of the event, or the number of not E divided by our total number. And the probability of an event plus the probability of not the event still has to add up to 1. Alright, so we're going to do a few examples here with some classic items that are used for theoretical probability. Coins, dice, and cards. So our first example says a coin is flipped, so what is the probability of getting, well, a heads, a tails, both, or neither? So here we can see a coin, the front and the back side, and we call this side heads because it typically has the head of somebody on it. This one has the head of Julius Caesar on it. It's a pretty old coin here. And then the other side we call tails. So based on just this information, we can determine the theoretical probability of different events happening. So if we want to find the probability of getting a head, we have to ask ourselves, how many outcomes are favorable to this event? Well, there's one head, so it's 1. And then out of how many possible outcomes do we have? Well, heads and tails, so there are 2 possible outcomes. So we have a 1/2 probability. We could also write this as 50% or 0.5. So what's the probability of getting a tail? Well, again, what's the question we ask ourselves? How many outcomes are favorable to the event? Well, there's 1 tail out of 2 possibilities. So again, we also get 0.5 or 50%. Now, one thing to notice here, if we have our 2 options, if we add up all of the probabilities, the 1/2 plus 1/2 for both of the outcomes, it's going to equal 1 or 100%. So what's the probability that you flip a coin and get both a heads and a tails? Well, it's going to land on one side or the other, and so neither side has both, so it's 0 out of 2 or 0%. And notice it means that it is impossible. It cannot happen. Okay, what's the probability of getting neither a head or a tail? Well, again, it's going to land on a side, and so we get a 0 out of 2, or again, 0%. It is impossible. Now, I know some of you are thinking, but it could land on the edge. Well, okay, we're not going to go there. Alrighty. Let's move on. In our next question, it says a standard six-sided die is rolled. So here we have a standard six-sided die, and what it is, it's a cube with the numbers 1 through 6 on it. So there's a 1, 2, 3, and 4, 5, and 6. Now the way it works is that the numbers opposite each other, well, there's a 1, and then the opposite side is going to be a 6, so they add up to 7. So here's a 4, on the opposite side, a 3, adds up to 7. And here's a 2, the opposite side's a 5, it adds up to 7. Okay, so the possible outcomes on a die, a six-sided die, are the numbers 1 through 6. So what is the probability of getting a 3? So we ask ourselves, how many outcomes are favorable to 3? Well, there's 1 3 on the die out of the total possible outcomes of 6. So it's a 1 in 6 chance of getting a 3. How about getting an even number? Well, we have a 2, a 4, and a 6. So there are actually 3 outcomes favorable to even out of our 6 possible outcomes. And so we have 1/2 probability, or 50%. How about not a 1? Okay, so what we want to do is go 1 minus the probability of getting a 1. Okay, so it's going to be 1 minus 1/6, which turns out to be 5/6. Now you could have also said, well, how many not 1s do we have? Well, the number's 2 through 6, so there were 5 out of 6 possibilities there. All right, what's the probability of getting a 7 on a six-sided die? Well, how many outcomes give you a 7? There are none. So 0 out of 6, or our 0%. This next one says a number less than 5. So less than 5 would be the numbers 1, 2, 3, and 4. So total possible for our outcome is 4 out of our possible of 6. So we'll reduce that to 2/3, or 66.7%. All right. Now this, of course, is just rolling one die at a time, and we'll talk about rolling 2 die and multiple die coming up a little bit later. Next, we're going to talk about playing cards. Now here we have a standard deck of 52 playing cards all laid out for you. Notice the jokers here have been kind of placed out on the side. Okay, usually we're not going to deal with jokers. And what we can see here is this is all of the hearts. So you can see what a heart looks like there. And these are all the diamonds. These are all spades. These here are clubs. And in each suit, okay, these are called suits. In each suit we have an ace, okay, which is also considered like a 1. And then we have the numbers 2 through 10. Okay, so you can see there's 7 hearts right here. And then we have 3 face cards. And they're the Jack, Queen, and the King. And that will be of hearts right here. And so all of this is in every suit. So you can see we have a total of 52 cards. Okay, hearts and diamonds are red, aces and clubs are black, and we also have a total of 12 face cards, 3 in each suit. There's also 12 cards in each suit. Okay, so it's going to be very important that you familiarize yourself with a deck of playing cards. Playing cards are great. Vegas is full of them. You got poker, you got 21 or blackjack, and lots of different stuff. And we're going to talk about card counting, and probability actually affects how card counting works. So if we had an entire deck of cards here, and we had them all turned over, and we wanted to pick one card, choose one card. What's the probability that that card would be red? When we say, how many red cards are there? Well, there's a total of 26 red cards out of how many cards in the deck? Well, 52. So that's one way of thinking about it. Another way of thinking is that there are an equal number of red cards and an equal number of black cards. So if we want to choose red, well, that's 1 out of the 2 colors, which is also 1/2. Okay, what's the probability of pulling a club? Well, how many clubs are there? Well, there are 13 cards per suit, so we know we have 13 cards out of a total of 52. Now, another way to think about that is that there are 4 suits. So we have our hearts, we have diamonds, we have spades, and we have clubs. So if we're thinking about this, that they're all equal, okay, then the clubs are actually 1 out of a total of 4. So this is what we're talking about when we say equally likely outcomes. So red and black are equally likely, and then the 4 different suits are also equally likely. All right, the next question says the probability of selecting an ace. So we just think, how many aces are there? There's 1, 2, 3, 4 out of 52 cards. Now another way to think about it, if all 4 suits are exactly the same, we have 1 ace out of the 13 cards. And so the probability is 1 out of 13. What's the probability of choosing a face card? Okay, well again, face cards, there are 12 total face cards out of the 52. Or again, we can think that there are 3 face cards per suit out of the 13 cards in the suit, so it's 3 out of 13. Now the next question says, what's the probability of getting a 10-point card? And this is used in blackjack. So a 10-point card is going to be a 10, jack, king, queen, or king. So these are your 10-point cards right here. And so there's actually a total of 4 per suit. Okay, so that can be 16 out of 52 or 4 out of 13. Now again, all of these can be changed into percentages, and of course you would have to round them, and these would be the exact probabilities right here. Another thing that we want to think about is probability can help affect our decisions on what to do, and it's very evident in card games. So in this game of Solitaire above, what is the probability that turning over the frog and the card being a face card? Well, now we're not dealing with the entire deck of cards. Because we know some of the cards that are turned over here, we can isolate which cards are remaining. And this is, in essence, what's happening when you're doing card counting. So, what's the probability of getting a face card? Well, how many face cards are left? So we already have 2 showing here. So we actually only have 10 face cards remaining. Out of how many cards are left that we don't know? Well, we know 1, 2, 3, 4, 5, 6, 7, 8, 9 cards, meaning there are 43 cards that we don't know. So we have a 10 in 43 chance of the next card being a face card. How about for a red card? So it's not going to be 1/2 because we can see the red cards. So we have 1, 2, 3, 4 red cards showing. So how many red cards are remaining? Well, there's 22 left out of the 43 cards that are still showing. Okay, what's the chance of the next card being an ace? Well, we already have 1 ace showing, meaning there are 3 aces left to go out of our 43 cards. Now with cards, we can also get more specific. So like a red queen. So there are 2 red queens, the queen of hearts and the queen of diamonds, and neither of them are showing. So we still have 2 possibilities out of the 43 cards that are left. And the last one, how about a club? What's the probability that we get a club? So I see 1, 2, 3, 4 clubs showing, and that means there are 9 remaining. So we have a probability of 9 out of 43. All right, so that is basic theoretical probability and how you can use it in a couple games of chance.